gridCONNEXT, rolling right into the next kind of 15-minute talk here. We're going into the functional area of real-time operations. So now I'm going to invite to the stage two speakers. Marissa Hummin is the Chief Technology Officer from Utilidata. And then also speaking, I don't know where he is, but Reynaldo Gomez is, oh, there he is. All right, is the Energy Partner Ecosystem Manager of NVIDIA. So take it away.
So I will be joined shortly by Ray from NVIDIA. Together, we represent grid operations and computation. So I think it should be a very interesting conversation for you guys. I've been doing real-time grid operations for about 12 years. I started off at the National Laboratories doing modeling of real-time operation of the wholesale markets, and I am now doing real-time operation on the distribution system. Can we go to the next slide? The rest of the world defines real-time operations as a heck of a lot faster than what we do on the distribution system. When I first started doing, or when the industries first started doing voltage optimization, we would print out voltage measurements from the edge of the grid. We would look at how to adjust a substation. We'd roll a truck and make an adjustment maybe a couple times a year. And that was better than nothing, but certainly nowhere close to where we need to get to. A consistent theme across the talks this morning is that the grid needs to change quickly, and we need to deploy those tools to get there. And I think from the perspective of what real-time operations means, if I can quote Commissioner Clements, Allison, we need to utilize every asset at every moment in time. So on the wholesale market side, we can get away with 5-minute dispatch, right? When you get down to the substation, we operate at about 5 to 15 seconds, and have for the last 10 years, where we dispatch voltage regulators and cat banks about every 5 seconds. But when you get to the very edge of the grid, the dynamics there require you to be in the sub-second realm. Which means, if we can go to the next slide, these are all just very illustrative. You don't have to read the text. Actually, there's no text. Which means we cannot fly a plane, aka the cloud, from the system operations room to each individual device at the edge of the grid in a sub-second time frame and expect that those devices are going to actually support the grid. So we all agree that there's lots of opportunity scattered throughout the distribution system to provide net services to our large-scale solar and wind investments, and therefore balancing load against variable generation. But the mechanism for getting there is something that we have really hesitated as a community to put our investment dollars behind. And I think that's largely because the way of our regulatory framework and the way we put in siloed regulatory filings in front of the commission, and the net technology really does need to work together. So Anterix is a really good example. The communication network will support grid operations, everything from operating devices for an economic outcome, all the way through visibility and restoration and recovery. So can we go to the next slide? We spent a long time on these clip art graphics here, trying to illustrate what is this missing piece between the end of the line, really the transformer at the end of the line, and all the things behind the grid. And that analogy I used of like we fly an airplane, that's about the time scale, right? If you shrink everything down, it takes seconds to minutes for you guys, for utilities today, to dispatch a DR event. And that DR event has an incredibly limited functionality, right? It might be, raise the temperature on the thermostats in the summertime to take a little bit of load off the grid, but it's certainly not to the point where it's a responsive system to a price signal. This is not merely a technology issue around communications. It's really about being able to process what's going on at the edge of the grid and contextualize that, make decisions at that location on a sub-second basis, and then execute. And that's a fundamentally different way of thinking about operating the grid than what we have today. But luckily, other industries have done this. And so I will turn this over to Ray to give us an example of how NVIDIA has helped solve this problem in other industries.
Thank you, Marissa. To drive home the point of real-time operations, I want to discuss another industry that NVIDIA has brought real-time to, and that is autonomous vehicles. What you see are just a fraction of the real-time operating models operating on real cars today. These vehicles cannot operate by sending 15-minute interval data back to a cloud to be processed once a month. They need real-time processing to happen at the point of measurement. In this case, the vehicle. They also need enough compute to be able to ingest dozens of high-resolution data streams, feed each of those data streams through multiple machine learning, deep learning, and physics-based algorithms, and determine the right action to take within milliseconds. This processing power is brought to you by GPU computing. Now, I know that using GPU compute for real-time operations may seem like an impossible leap for the electric utilities, but I'm here to tell you that it's not. It's really a natural evolution from where you're at today and the current state of many other industries, including healthcare, manufacturing, telcos, cybersecurity, finance, and more. The path to real-time operations that we took NVIDIA through is going to be directly analogous to the path that the electric utilities take. So I'm going to walk you through the journey that we took that industry through. It all begins with data collection. Now, for a car, this means outfitting an existing vehicle with an array of cameras and sensors and driving it around for thousands and thousands of miles to collect that data. Once those data are collected, they're then cleaned up and labeled. I'm talking things like stop signs, street lights, highway lines, pedestrians, etc. Once you've got a collection of clean labeled data, then the real work can get started. That is where you feed those labeled data through all of your different AI models, so that way they can begin to learn the world around them. This process is called training a model. And once you've trained the model on existing data, you have to test and deploy it on new data that it hasn't seen, so that way you can gauge how it is able to react. Obviously, you can't jump straight to the real world, so you have to deploy these on virtual cars in a simulated environment, essentially a video game. These models are tested, they're expanded, they're refined, and eventually they get to the point where you can deploy them on a real car. Today, through partners like Tesla and Daimler, I am happy to say that NVIDIA has helped push real-time operating models on real cars on real roads. Now, the path that we want to take the electric utilities through is going to be very similar. It all begins with data collection. Instead of outfitting a car with cameras, we're going to outfit existing meters with meter callers that contain edge GPUs, so that way they can process, analyze, and collect the high-resolution voltage data that's streaming in from the grid. Now, this is vitally important for this industry because current smart meters today, they either don't sample at a high enough resolution, or they do sample at a high resolution, but then almost immediately downsample and then send that coarse data back to the utilities. So there is no collection of really high resolution voltage data that streams through the meter. It is vitally important that we change that by deploying small pilots of these meter callers, so that way we can begin collecting the data. Once those data are collected, they'll then be combined with other data sources like market signals, home appliances, and DER. Those labeled data will then be used to train different models for real-time operations that will enhance grid resiliency, increase decarbonization, and eventually lower consumer bills. Those models will be tested and deployed in a simulated environment, refined further before they're then pushed back out to the meter callers. The meter caller pilots will expand from hundreds of meters to hundreds of thousands of meters, and we will gradually ramp up the real-time operating capabilities and controls of the meter, eventually turning it into a distributed compute node for real-time operations of the grid. Now, I know everybody here has heard these promises before. You've been hearing them for the last 10 to 12 years, and they've largely failed to come to fruition for several reasons. In my opinion, one of the largest is the lack of compute. It is ridiculous and unethical to promise a wealth of functionality on a $4 microprocessor that was only designed with accurate billing in mind. We need to get used to the idea of deploying additional compute at the grid edge so we can run additional models, additional applications, and drive additional value back to the consumer.
Powerful statement.
Yeah, pretty powerful. and to help you avoid mistakes moving forward and deploying antiquated technology, I want to leave you with 2 questions to help you penetrate through smoke and mirrors and determine if an edge device is going to be capable of real-time operations. 1, what is the compute that is powering this device? And 2, what is the performance of that compute as measured in TOPS, or trillions of operations per second? That is the metric used to determine the processing power of edge devices. Now, unless they're able to deliver at least 10 TOPS of processing power, they are not going to be able to run multiple models, multiple applications in real time, and deliver the functionality that the utilities and the consumers deserve.
Go to the next slide. So, by the way, that's the enthusiasm we need in the energy industry, which is why we're partnering with NVIDIA. They've done this before, and bringing that technology and innovation into our realm is what we need to do. I think I want to close on the perspective that real-time grid operations is possible. The technologies exist, the fundamental technologies exist for computation and communication and storage, and the software layer that connects that has been in operation in various parts of the grid for the last 10 years and is ready to be deployed at the edge of the grid. And so I challenge us as a community to start thinking about how we write our filings, how we write our policies and regulations, so that the concept that we deploy real-time operations with every single aspect of the evolution of the utility is fundamental, is built in. There you go.
Thank you both. I think I have one big question here that maybe both of you could take a crack at. So I think it's really interesting, taking examples, case studies from other industries where we see similar needs and similar functions that we want to kind of bring over to the electric grid to help see it, to help operate it better. What do you think are the biggest challenges you might foresee in making that transition, and not only the challenges you foresee in kind of pulling it over to the grid space, but also have there been any kind of just demonstration studies that are trying to start applying this that you might find some challenges along the way, or is it something you are looking to roll out and maybe right now it's just conceptual challenges?
I think the biggest challenge is data, and the resolution of the data and the density of that data over a geographic area just frankly doesn't exist. Nobody has put out measurement devices at every endpoint within a circuit and used that to start running that circuit differently, right? So as a grid operations company, we're lucky if we get 15-minute data a day late, right? And you can do a lot with that. I'm not saying you can't, but that is not the same thing as running the grid in real time. So I think the biggest problem is data, and that means that we need to start in a speculative manner, which was not something this industry does very well, putting out technologies that allow us to collect that data. And then I think the second thing is the way the investments we make today are going to be present on the grid for the next 10 to 15 years. And we need to start taking chances with that technology. That means on the regulatory side, we need to give a little bit more rope to the utility to step outside their comfort zone. If we require a 10-year study before you can put your cost-benefit analysis together and file it, we will deploy 10-year-old technology. If you want to be ready for 2030, we need to step outside of our comfort zone. So
I would just like to add one other challenge that I see from the NVIDIA perspective, and that is the closed proprietary systems that have really dominated the market over the last 12 years. I think we need to enable open platforms so that way a utility who deploys a solution from hardware vendor A can deploy applications from vendor B, can deploy applications that are developed from their own in-house data scientists, and the consumer can also choose what other third-party applications get deployed on their meter. I think we need to open up these platforms so that way we can enable more competition and more innovation.
Well, Well, I don't think there's a better transition to what the next 15-minute talk will be. But thank you to you both. This has been really exciting. We're about to just run into a 15-minute break, so we'll meet back here in 15 minutes at 3:45. So let's give these two a huge thank you and round of applause.